Great to see you here. My name is Luc de Ceuster, founder of the Ceuster Academy, and I'm here today to offer you a new video. This video is about solving linear congruences. But before we start, do not forget to click the subscribe button, click the bell button, so whenever we have a new video, YouTube will inform you about it. Linear congruences are equations of the form AX is congruent B modulus M. We've seen congruences before and we can work with those congruences. Now we have to find the parameter X. What value of X satisfies this equation? Now, when we look at the theory, and there are a lot of proofs about how to resolve the linear congruences, and I will not give you the proof, but I will only give you the solution, the result of it. We can say that a linear congruence of this form has one unique or more solutions modulus M when the greatest common divisor of A and M divides B. When that is true, then there are the GCD of A and M solutions, and those solutions are separated by M divided by that GCD. That's the general way to resolve this type of congruences, but there is one special case where the GCD is equal to 1. In that case, we have a solution for whatever value of B, and we can prove, and it has been done, that then there is one unique solution, and that unique solution is modulus M. And we will see in the following parts of this video how we can do the calculations, how we can find those different solutions. The first solution, the first case, is when the GCD of A and M is equal to 1. This also means that the A modulus M is inversible. It means that we can find the inverse of A modulus M, which is A bar, or sometimes also written as A minus 1. And what does it mean? It means that A times A inverse is congruent to 1 modulus M. Or this also means that A or 1 M divides, M divides A times A inverse minus 1. Now, finding the inverse modulus M is in fact the way to solve this equation, because what will be the final result when we find the inverse? Once we find the inverse, we can multiply this expression both sides with the inverse of A modulus M. So what we have now, A inverse times A, X, is congruent with A inverse times B modulus M. And we know that this one in modular arithmetic will be equal to 1. So we have to find here the lowest number of A inverse multiplied with B, and we have one unique solution, modulus M. And we always take as a solution the lowest number, so we have to find A inverse times B modulus M. That will be the solution. That's one way to resolve this problem. When we have the second case, the GCD of A and M is not equal to 1, so they're not, or A modulus M is not inversible, we have two possibilities that we can use to resolve this congruence. The first element what we can write is when we take the equation, we can say that the M, the modulus M, divides AX minus B. So this is generally true for all congruences. And what we can write based on this, we can say that A times X is K times M plus B. And K is an element of Z plus we take the positive numbers here. So we can start from 0, verify that Ax is equal to B, and if x is an integer, then we have a solution. And we do that the number of times that it is necessary. Like we said before, we have GCD A of M solutions, which are all separated by M divided by the GCD of A and M, like we saw before. So that's one way to resolve this problem. A second element that we can do is that we can say, can we write this congruence in the form of, and I take another color, C times A times X is congruent with C times B modulus M. Since we have a constant here, what we can do is in fact divide both sides, divide by C, which would give us a result which is AX is congruent with B modulus M divided by the GCD of C and M. And once we have this, we will find here a new solution where the GCD of this A and this M will be equal to 1, which brings us back to the first solution. So we've reduced the problem, we brought it to a different modular space, but in this modular space the equation that we find has a solution which is the same as for the general congruence. So basically what we find here, we find the first solution of this congruence. And of course, we can then find the follow-up, the other solutions which are separated by M divided by the GCD of A and M. So basically those are the things that we're going to do, and we're going to apply that on our different examples. When we're trying to find the inverse of A modulus M, we can go back to the Euclid algorithm, the extended Euclid algorithm, where we found the expression of the GCD as a linear combination of the parameters A and M. S and T are the Bezout coefficients. Now, in case the GCD is equal to 1, when that GCD is equal to 1, we can prove that S will be the modular inverse. Let's have a look at that. So we replace this in the expression, so we can say that the S times A plus T times M is congruent with 1 modulus M. So basically that's the relationship that we have when we have the modular inverse. And when we look at this, when we look at the modulus M, we know that Tm is congruent with 0 modulus M. So basically in the modular arithmetic, this becomes equal to 0. And the final expression that we have, SA is congruent with 1 modulus M. This means that S is the modular inverse of A. So what we're going to do when we have the GCD equal to 1, we are going to find the Bezout coefficients, and when we find the Bezout coefficients, we will find S, which will lead us immediately to the modular inverse. Let's do that in a simple exercise. So this is the congruence or the linear congruence that we're going to try to find a solution from. 4 is 1119x is congruent 3 modulus 5412. Now, we already know I've chosen this exercise that the GCD of 119 and 5412 is equal to 1. So basically we will find one unique solution. But the first thing we have to do is try to find the Bezout coefficients. And well, first apply the Euclidean algorithm on this side here, on the right-hand side of the board for you. And let's start with it. So what I can say is that 5412 can be written as 45 times 119 plus a remainder of 57. We can continue with the Euclidean algorithm. Now we say 119 is 2 times 57 plus 5. And we continue. Now we have 57 is 11 times 5 plus 2. 5 is 2 times 2 plus 1. And finally we find 2 is 2 times 1 plus 0. So we find the GCD here. And from this we will start the backward path. When we write the backward path, the first thing to do is to express everything as a function of the GCD. So the left-hand side is the GCD, so I can say 1 is 5 minus 2 times 2. Now we go to the next equation here, from the second equation that we have. And from the second equation, I can say that 2 is equal to 57 minus 11 times 5. And I put that in this equation, and I will give you immediately the result. So I don't have enough space to do all the calculations here, but we see that we find 5 minus 2 times 57 minus 11 times 5. So basically what we find here is a new expression. So we have 23 times 5 minus, and here we have the remainder part, 2 times 57. So what we have here, we have 2 minus 2 times 57, so we have 2 times 57, minus 2 times minus 11 is 22, plus 1 is 23. Now we continue. The next element that we are going to put there is from equation 3. So here we can say that 5 is equal to 119 minus 2 times 57. And we replace 5 in this equation. So what we find now, and I will do it completely here, 23 times 119 minus 2 times 57, and we have here minus 2 times 57, which gives us a total of 23 times 119 minus 46 minus 2, 48 times 57, and from here we can go to the last equation, to the fourth equation, and that fourth equation tells us that 57 is equal to 5412 minus 45 times 119. And when we replace that here, and here I have to look at the board, I find a total of 2,183 times 119 minus 48 times 5,412. what we can conclude from this is that we can say that the GCD of 119 and 5412 equals to 1, and we can say that this is equal to 2183 times 119 minus 48 times 5412. And when we look at the coefficients, this is S and this is T, which means that 2183 is the modular inverse of 190 modulus 5412. And we will continue with that to find the final solution of this linear congruence. Previously we found that 1 equals 2183 times 119 minus 48 times 512, which are the Bezout coefficients for this GCD. S is 2183 and T is 48. We've proven before that in this case 2183 is the modular inverse of 119 modulus 5412, and we can write that 119 multiplied with its modular inverse 2183 is congruent with 1 modulus 5412. In order to find the solution, we have to multiply this expression with the modular inverse. So we find that we have 119 times 2183 is congruent with 2183 times 3 modulus 5412. Now we know that this modulus 5412 is equal to 1. So what we're going to do now, we can say that 1119 times 2183 is modulus is congruent with 1 modulus 5412. So basically, oh, I forgot the x here. This has to be with x. So this is 2183 times 119 times x. So we can see that x is, or say that x is congruent with this 2183 and 2183. I do the calculation quickly. 6,300 to 40 and 9, so we have 6,549 modulus 5412. And we can also say that 6,549 modulus 5412 is equal to 1,137, if I'm right. Yes. So what we can write now is that x is congruent with 1,137 modulus 5412. So basically this is our solution, and this is the solution to this linear congruence. Of course we have everything, all the solutions are modulus 5014, so we can also say that x is equal to 1137 plus k times 5412, and k is an element of z. So basically we have all those solutions, but they're unique modulus 5412. So this was an example where we had, in fact, the GCD of 119 and 5412 equal to 1. It means that there is one unique solution, and of course this GCD, which is 1, always divides 3, and basically we can find the solution here. We can find the value for x for any number that we have here. Let's do another exercise where the GCD is not equal to 1. Let us now consider a linear congruence where we already know that the GCD is not equal to 1. And let's just take the GCD here, GCD of 6 and 21 is equal to 3. We have 2 times 3, 7 times 3, so that's the greatest common divider of both of them. So basically what we can say, there are 3 solutions only when the GCD divides 15, and we know that the GCD of 6 and 21 divides 15, so we have 3 solutions, and they're divided by m divided by the GCD of 6 and 21, which is 21 divided by 3 is basically 7. So we have 3 solutions. There are solutions. We have 3 solutions divided by 7, all modulus 21. So these are the different possibilities that we have to find here. Let's now have a look at all of these elements. The first way to resolve this is write this as 3 times 6x is congruent 3 times 5 modulus 21, and I can say that this is 7 times the GCD of 3 and 21, which is 3. Now we divide both sides by 3, so I find, oh sorry, this is not 6x, this is 2x. It's easy to make mistakes on the board, so we can say that 2 is congruent. Another one. 2x is congruent with 5 modulus 7, and when we look at this, we know that in this case the GCD of 2 and 7 is 1. It's very clear because these are both prime numbers. Prime numbers have always a GCD equal to 1. So now we have the equation 2x is congruent with 5 modulus 7. The GCD is of 2 and 7 is 1, which we can use now to find the modular inverse, and we will need the modular inverse to multiply with this expression to find the formal, or the let's say the final solution. So what we find here is that we have 7. When I look at it here, we can say that 1 is equal to minus 3 times 2 plus 1 times 7. These are the Bezout coefficients. We're working in modular 7, so we can say that the modular inverse of A is 7 minus 3 is basically 4. Now to find the solution, we have to multiply this equation with 4. So we find here 4 times 2x is congruent with 20 modulus 7. We know that 4 times 2 in the modular space gives us x, and we find 20 modulus 7. I can reduce this because this is 2 times 14 plus 6, so we can say that this is 6 modulus 7. And the first solution that we have here is 6. 6 is the first solution. We know that we have 3 solutions separated by 7, so the second solution is 13, and the last solution is 20. Of course, all modulus 21, we find those different solutions here, and we see when we put again 7, we find 27. 27 is the same, 27 modulus 21 is the same as 6 modulus 21. So we see that after the third number here, we see a repetition of those numbers. But let's now have a look at a different way to resolve this equation. Let's now do the same linear congruence and try to find it in a different way. Now we know that from the definition of a congruence, we can say from this expression that 21 divides 6x minus 15. And before we already found that there is a other relation we can deduct from this, that we can say that 6x is 21 times k minus 15, and k is an element, let's say, of z plus a positive integer starting from 0. Now when we're going to look at this, we're just going to replace k by different values and see if we can find an integer value for x. K equal to 0, so basically what we find here, 6x is, and this has to be plus 15, sorry for that, 6x is equal to 15, and there is no integer x that complies with this. So this is not a possibility, no solution here. K equals to 1, then we have 6x is 21 plus 15 is 36. So here we find a solution because x is equal to 6. So that's our first solution for this linear congruence. K equal to 2, we find 6x is 2 times 21 is 42 plus 15 is 57. So there is no integer value for x. We continue for k equal 3. So we find now 6x is 21 times 3 is 63 plus 15 is 78. So we find now an x value which is equal to 13. And we find k equal to 4, and we see that 6x is 4 times 21 is 84 plus 15 is 99, and there is no integer value for x. Now we find k, or we go and verify for k equal to 5. So we see 6x is 5 times 21 is 105 plus 15 is 120. So now we find x is equal to 20. Now we can continue for x equal to 6. We will see that there is no solution. And for x equal to 7, we will find 27. But 27 modulus 21 is again 6. So basically we found the 3 solutions modulus 21, which are a solution for this linear congruence. That was it, the introduction to linear congruences. We tried to find the solution x. We looked at the rules that apply when we have a solution or multiple solutions. What are those solutions? How are they separated? And we also saw the special case when we have a GCD which is equal to 1. In that case, we have a unique solution modulus n. it's the end of this video. Do not forget to have a look at our offers in the text below. We have links to our different courses that are available today on our website. There is a coupon linked to every course that will give you a great discount. Anyway, do not forget to click the subscribe button, click the bell button, so every time we have a new video, YouTube will inform you. It was great seeing you here. I hope you liked the video. If you have some questions or comments, just put them below. I'm looking forward to seeing you in our next video. Thank you and bye-bye.